Welcome to the second session on equalization. In the previous class, we have seen what is zero forcing equalizer, what is MMSE, minimum mean square equalization, what are the algorithms that we are going to apply to make our received signal free from inter-symbol interference. Right? We have seen what is called as a linear equalizer. Why do we call that as linear and non-linear equalizers? What are the two basic structures? We have not seen the structures in detail, but we have understood what is the structure, transversal and lattice structure for equalizers. So let me give you a small recap of what we have done in the previous class. The objective was that inter-symbol interference should be eliminated or reduced. So in linear equalizers, we had a big problem called what happens is that the noise is also enhanced. In zero forcing algorithm, in MMSE, all these things, the input signal to the equalizer will contain both the transmitted signal and the noise. And both the noise and the input signal both are enhanced. Okay, that was what we have seen for both zero forcing and MMSE, minimum mean square error equalizers. Okay, today we'll be seeing what is called as LMS algorithm, least mean square algorithm, and adaptive equalization. We'll begin with what is a least mean square algorithm. But before that, I'll give you an introduction to adaptive equalization also for your understanding. In detail, we'll study in the last 2 or 3 slides about what is adaptive equalization. You know that a wireless channel is time varying, volatile and unpredictable. There can be a lot of different happenings or events that happen in between the transmitter and the receiver. Okay, so we need to build up an equalizer which is adaptive. That means that we need to have an equalizer. We need to have an equalizer which is able to understand the wireless channel. We have given that C of t, right? In the previous session, C of t, the response of the channel. So the response of C of t is highly volatile and keeps changing with time. An adaptive equalizer is something that is capable of adapting to these changes. That means that the equalizer algorithm gets automatically updated based on the channel conditions. Okay, this type of equalizers are called as adaptive equalizers. Least mean square algorithm is a type of adaptive equalizer whose methodology or whose algorithm or the steps we'll be seeing as we go on. Is that clear? So in the last class we have drawn this diagram, basic diagram of a digital equalizer. This is the same diagram. This is going to give you an introduction. As I told you already, we have an input decay passing through a channel. We are pulse shaping this with GT and passing through a channel which has inter-symbol interference, and the response of the inter-symbol interference is C of t. Here adding it with the noise, additive noise or the colored noise. Okay, and then through the RF front we are getting the signal to be W of t. After, since we have a pulse shape, we are using a masked filter and then you are sampling it, giving to the equalizer the output of the equalizer decay. And here we have a regular updates to the algorithm. So as is the case with minimum mean square or any other kind, the objective of our equalizer design is to minimize the error. Okay, minimize the squared error. What is the error? Error is the difference between the received signal and the output of the equalizer. Okay, so what we are doing is that we are having a transmitted signal, symbol dk, the output is dk, the output of the equalizer. So our objective in design of this equalizer is to reduce the difference between these two values, that is dk minus dk cap square. So now let me explain to you what is the working behind the logic or the working principle of LMS algorithm. LMS algorithm is also known as stochastic gradient algorithm. You have the input parameters xn. We are going it through an adaptive filter. We have something called as en. So the objective as usual is to minimize the error en. So the basic block diagram for a LMS algorithm is given in the screen. So let us define the prediction error EK. EK is given as the input signal x of k minus yk transpose into wk. Wk is the coefficient that is going to determine the properties of our equalizer. Okay. So this is the prediction error. Let us define mean square eta. Eta is actually nothing but eta is equal to the modulus of ek square, or in other words, this is equal to expectation E of ek conjugate. Okay. Eta E expectation of ek and ek conjugate. So as explained already, the objective of our algorithm or LMS algorithm is to minimize the mean square error. Certain functions to help us understand how we are going to minimize or reduce this and find out the optimal tapping coefficients. So let us define a cost function like what we have done for minimum mean square. We'll call it as j omega and jwn, and we'll denote this jwn will denote the mean squared error as a function of w or wn. Okay. If P is defined as the cross correlation vector between the desired response dk and the input signal y of k, and Rn is the correlation matrix of the received signal, then now we can set the gradient of J, W, N to 0. How we'll do that? We'll do the partial differentiation of Jn and we'll set this to 0. To obtain the optimal value of W, we need to find an optimal value, right? Wn, we call it as W opt or something like that. So our objective is to find out the optimal value of W. So what we'll do is that we'll take the partial differentiation of this function with respect to Wn. At that case, on solving, you will get it as minus 2pn plus 2rnn wn, which we are equating to 0 to find out the optimal value of wn. Okay? When we do it, what happens? Is 2 and 2 cancels and pn on the side, pn will be equal to rnn decide wn, right? Wn is the equalizer coefficients, right? This is a very important equation and this equation is called as normal equation. Since the error is minimized and is made orthogonal, that is, it is made normal to the projection related to the desired signal x of k. This equation is called as normal equation because we have brought the error to the minimal level and the signal is orthogonal or E is perpendicular normal to the projection related to the desired signal x of k. So next case, we are equating it to 0 and we are going to find out the optimal J opt, which is nothing but J as a function of the desired Wn, which is nothing but E x conjugate into x minus Pt desired Wn. So we are going to optimize the value J so that we get the ideal values for Wn. To obtain the optimal tap gain Wn, the normal equation what we have derived in the previous slide or what we have written down in the previous slide has to be solved iteratively. Iteratively means continuously. Up to how much times? N times or n minus 1 times, because it has to continuously keep repeating, right? Till the number of taps is being achieved. As the equalizer converges, this is a principle of convergence. Equalizer converges to an acceptably small value of J opt. Optimal value of J. So let us define a variable or let n denote the sequence of iterations that LMS is going to compute n number of times. These are the steps that it has to repeat till we get the optimal value of J opt. Okay. So Ek of n is given by xk of n. Already we have defined this. Now the error is defined as the input signal minus the output of the equalizer or the desired output of the equalizer. From then what we'll get is that we'll get Wn n plus 1. So n is the number of times it is being repeated. We'll have another one, additional one, right? Is equal to Wn of n minus alpha e conjugate, ek conjugate of n into yn. So this is very important equation which is going to define the optimal coefficients. The n subscript denotes the number of delay stages in the equalizer. We know that every equalizer we have the stages now. Last time we have seen that equalizer works like this, right? You have a system like this, right? Yes or no? You remember that? So imagine that we have an n stage equalizer. We are summing up all these values, right? We are summing up all these values, and in that case we'll presume that n is the number of delay taps in the equalizer, alpha is the step size which controls the convergence rate and the stability of the algorithm. We know that the desired decay of n will be Wn transpose into Yn, right? It's already defined. The LMS equalizer minimizes the signal to distortion ratio at its output with the constraints of the equalizer filter length. Okay. So what it does is that we are finding out J opt, and we can note that the Wn is W of n plus 1. W of n plus 1 is not related to or does not have any distortion components, noise components in its equation. So what we come to understand is that this LMS equalizer minimizes the signal to distortion ratio. If the input signal has a time dispersion characteristics that is greater than the propagation delay through the equalizer, then the equalizer will be able to reduce distortion. In the previous two examples, we have seen zero forcing and MMSE. In both these cases, we have come to understand that there is no reduction in distortion. But LMS is an adaptive equalizer where we have distortion reduced. That is why these points are important. Whenever you are asked to write the significance or whenever you are asked to describe the steps with respect to LMS algorithms, you need to mention all these points for you to get better marks. So what is convergence rate of any algorithm? The convergence rate of LMS algorithm is low due to the fact that there is only one parameter, the step size alpha, that controls the adaptation rate. Okay. Convergence rate is slow because we have only one factor that controls, that is alpha. So with this, I believe we have understood what is LMS algorithm. These are the steps that you have to write when you are asked about LMS algorithm. Now, already in the beginning, in the introduction to this class, I have given you what I have made you understand what is adaptive equalization. We know that the channel is time varying and is volatile. So, adaptive equalization, I have already given you an introduction. An adaptive equalizer compensates for an unknown and time varying channel. It requires a specific algorithm to update the equalizer coefficients and track the channel variations. So what we do in adaptive equalization, not only this, we have another one more called as RLS, recursive least square RLS algorithm. Is another type of adaptive equalization algorithm like LMS algorithm, but we will not be seeing RLS algorithm in detail because we don't have it in our syllabus. Okay, so any adaptive equalizer algorithm, what it does is that it understands the variations in the channel and then it tries to update its own filter coefficients according to the changes in the channel conditions. Okay, so we are assuming that C of t is the response of the channel, and what happens is that when there is a change in the response of the channel, the equalizer is capable of adapting itself to a new set of coefficients. This is called as adaptive equalization. So the channel response C of t is generally not known when the receiver is designed. The equalizer must be tunable so that it can adjust to the dynamic conditions of the response of the channel, denoted by C of t. When the equalizer coefficients are updated periodically to estimate the channel, the process is known as adaptive equalization. There might be questions like, what do you understand by adaptive equalization? Or explain how an adaptive equalizer works. Or explain what is the need of adaptation. Why do we want to adapt? We need to adapt to the conditions because we have a time varying channel. You are having a tower, you are having a receiver. There is a channel, wireless channel. This particular wireless channel can have so many varying conditions. It can rain all of a sudden. When it rains, it changes. So imagine there is a tower and there is a receiver, mobile here. This is a transmitter and this is a receiver. Okay. When the signal is transmitted from the transmitter to the receiver, there can be a lot of variations in the channel. And this channel response is adopted at every period of time. There is a time gap and it is updated very periodically. There could be rain, there could be so many other things that interrupt the transmission and the reception process. The performance of adaptive algorithm is determined by the following four steps. Not these four steps, these are the major points. There are more other factors that adaptive algorithm gets influenced by. One is called as rate of convergence. Misadjustments, computational complexity, and numerical properties. So these are the four major factors that influence the adaptive algorithm. So with this we'll be concluding 4.2, the second part of the fourth module that deals with equalization. Okay, entire equalization is very important because it's a vast area of research is going on in equalization. Equalization helps to enhance the received signal. So thank you all. Thank you very much for listening to me. Thank you very much.